By monitoring the concentration of a reactant over time, we can calculate the average rate of a reaction over any time period during the course of the reaction. For example, in the reaction of bromine with formic acid, bromine concentration is monitored and is plotted against time. For any 2 points on the curve, a triangle is formed. The two sides of the triangle correspond to the change in bromine concentration along the vertical axis and change in time along the horizontal axis. The slope of the hypotenuse of the triangle formed is the ratio of the two, which is the average rate of the reaction over that time period. Of course, the negative of it. The average rate is equal to negative of the change in bromine concentration divided by change in time. This is the graphical method to calculate average rate. You can change the time period to be along any time change, and you would get the rate corresponding to that time period. Also note that as the reaction progresses, the rate decreases. As concentration decreases in a nonlinear fashion, for a given amount of time, the rate of change of concentration is going to decrease. Eventually, this line is going to be horizontal, meaning that the rate of change of it is zero, meaning the reaction rate is zero, meaning that the reaction has stopped. The average reaction rate can also be calculated from the measured concentrations at certain times during the reaction. For example, in the first 50 seconds of the reaction, concentration changes from 0.012 to 0.0101. Therefore, the average rate in that interval is a negative of the change in concentration over change in time, which calculates as 3.80 times 10 to negative 5 molarity per second. For the first 100 seconds, the average rate is calculated in a similar manner. The change in concentration is divided by the change in time. The average for the first 100 seconds is 3.54 times 10 to negative 5. The rate is expected to decrease with time, and we see that from the calculated values. Please note that the rate values given in this table are instantaneous rates at that specific instant during the reaction. We are going to discuss instantaneous rates next. Now calculate the average rate of the reaction between the first 100 and 150 seconds of the reaction. Here's another practice problem for you to solve on average reaction rates. As you shorten the time period over which rate is calculated, delta t approaches zero, and the rate equations give us the instantaneous rate. This is the rate for a specific instant during the course of the reaction. Instantaneous rate can be calculated in two ways. In one method, the graph of concentration versus time is used. The slope of the tangent to the curve at a point in time is the instantaneous rate. The other method uses the rate law, which is the mathematical relationship between rate and the factors that affect it. You will be learning about the rate law in the next section. Let's see what kind of information we can extract from the concentration profile, the change of concentration against time for a given reaction. How can we compare the instantaneous rates at point A and B? Imagine the slope to the tangent to the curve at point A and point B. At point B, the tangent is going to have a smaller slope. Therefore, instantaneous rate is lower in point B. Therefore, the rate for this reaction is not constant at all points in time. Rate continuously decreases. How about a reaction concentration profile given in this graph? The rate is the same at both A and B, and the rate of this reaction is constant, does not change in time. These are two cases of the concentration dependence of reaction rates. The first example shows a reaction where the rate is dependent on concentration. As the concentration decreases, rate also decreases because the slope decreases. But the second example shows a reaction where concentration does not affect rate. Rate is independent of concentration. As concentration of the reactants decrease as they are used in the reaction, Rate does not change. Rate is constant. The decrease of concentration is linear. Here's a final comparison between average rate and instantaneous rate. In this example, we are looking at the rate of formation of oxygen, a product in the reaction. This is why concentration is increasing over time. Average rate is calculated over a time period during the course of the reaction, any time period. For the formation of oxygen, average rate is calculated at two different 600-second intervals along the path. Using the same curve, instantaneous rate can be calculated using only one point along the curve, an instant. The slope of the tangent to that point is the instantaneous rate at that instant.